Hi everyone, welcome back. Today we're going to be talking about differentials and linearization approximations. Now in this particular section, I'm going to start off with linear approximations. And these linear approximations are basically going to be a way for us to approximate a given function at a given point or near a point, so long as we're able to find its tangent line. Now, of course, the tangent lines that we're going to be looking for, well, those are linear equations, and therefore we're going to be able to extract, or we're going to be able to identify that a linear equation can approximate a function, so long as the function doesn't move or doesn't stray too far off from the point in question. So here we have a function, and then we're going to have a tangent line to that function. This tangent line serves as an approximation to this function, but it only serves as that approximation near this given value, which we'll call a. So as long as your x values are near a, this is going to be a good approximation, meaning that this line is going to be a good approximation to this given function. Now, what we're going to be focusing on is going to be to extract or to generate the equation of that line. So if we have an x value of a, then naturally this ordered pair for that point then becomes a and f of a. Well, if we want to find the equation of a line, finding the equation of a line, we would need to use y minus y1 is equal to m times x minus x1. Again, we're using the point slope form of the line to find this equation of the line. Now, identifying that if we want to find the equation of that tangent line, then from the previous sections, we know that if we take the derivative of the function and evaluate that derivative of the function at the value of a, then naturally we're going to get the slope of the tangent line. So this new equation with all of our substitutions then becomes y minus f of a is equal to the slope of the tangent line, which that's going to be f prime at a, multiplied by x minus x1, where x1 is a. And so we get this new equation here, and if we want to get the equation of the line, of the tangent line, then we get y is equal to f prime at a multiplied by x minus a plus f of a. This is that equation of the tangent line, but more specifically, this equation of the tangent line is going to approximate this function near the value of a. So the way we write this for this linear approximation is going to be in this way. That the linear approximation of f of x near a is that f of x is approximated to be this function that we found, which is f prime at a multiplied by x minus a plus f of a. Okay, so that's great. So we get this linear approximation. Now we want to streamline this a little bit more. Instead of saying that we want to find this linear approximation, what we're going to say now is that the linear, or the linearization, I should say, So the linearization of the function f of x at a is, we're going to use the notation L of x. This linearization means that we're going to take that linear function that we found and we're going to assume that's going to, or we're going to know that it's going to approximate this function f of x. Therefore, it's called this linearization, which is this function that we were looking at right above. And so this is where this whole process of linearization or linear approximations stems from. So what we get here, or what we get to see, is that we get to see that f of x is approximated by the linearization L of x, so long as when x is near the value of a. In other words, that x value in question. And so this here again was the curve that we were looking at, and this here is the tangent line. So let's put this to use. So here goes this question, where we want to find the linearization to f of x, which is equal to the square root of x, at x is equal to 1, and use it to approximate the square root of 1.1. All right, so we're going to go into it and we're going to dissect everything that we need. So first off, we have the function. The function is the square root of x. They're giving us a value in which we want to calculate the linearization for, which means if I need the linearization, if I need this linearization, then the linearization equation is f prime evaluated at a times x minus a plus f of a, which means we need to evaluate a few items here. Number one, we're going to need to evaluate the function at x is equal to 1. That's our a value. So the function evaluated at 1, that's going to be the square root of 1, which is 1. Great. I need my derivative. So I'm going to say f of x is equal to the square root of x, which is equal to x to the power of 1/2. So finding that derivative would imply that I use the power rule, drop the exponent forward, subtract 1 from the exponent, and let's simplify this to be 1 over 2 square root of x. Now that we have the derivative, we need to calculate the slope of this function, of this linearization, by evaluating the value of 1. In other words, f of a. So making that substitution, we get that f prime at a is 1/2. Therefore, the linearization that we are looking for, this L of x, is going to be f prime at a, which we found to be 1/2, multiplied by x minus a, which in this case is 1, plus f of a, which was 1. Let's simplify this. We get 1/2 x minus 1/2 plus 1, which means the linearization is 1/2 x plus 1/2. Awesome. This is that linearization that we're looking for, meaning that this function, this square root function, can be approximated by this linearization only for the x values that are near 1. And now we're going to use this linearization to approximate the square root of 1.1. So using the linearization, oh, and by the way, we answered the first part. So using the linearization now, I'm going to approximate 1.1 because 1.1 is relatively close to 1, therefore we can approximate it. In doing so, I'm going to be substituting in here, L of x is going to be 1.1 is equal to 1/2 multiplied by 1.1 plus 1/2. And in this instance, all we want to do is make our substitutions here. When we make our substitutions, right, we're going to get something real nice here. We're going to get 1.05. And this is that approximation that we're using for the square root of 1.1. Just for fun, let's see if we can extract from the calculator. So from the calculator, square root of 1.1 is approximately 1.0481, which means, is our linearization a good approximation? It definitely is. And that's why we want to use these linearizations. In order for us to be able to consider these approximations, we want to first find the linearization, make this a nice linear function to evaluate, and therefore it's going to be easier to calculate. Awesome. So that's the first part of this lesson. Now we're going to go on to differentials. So here's your definition for a differential. We're going to say let y equal to f of x be a differentiable function. The differential dx is an independent variable. The differential dy depends on that differential dx, and therefore dy is equal to f prime of x multiplied by dx. Now, this is very interesting to look at or to establish, because what we then want to see, or what we then want to do, is we want to interpret this differential function, or this whole differential process, as dy is equal to dx. And if y is equal to x, then that means that this must mean that I'm taking the derivative of the function. And what's happening here is that we're essentially taking the derivative, or in this case, calculating that rate of change. The change in y over the change in x is equal to the change of the function at x. Therefore, we can treat that differential as some numeric value. And when we treat it as some numeric value, then we can establish this definition that we're observing here. And we want to use that definition for a differential for dx or dy in order to establish more properties that are going to be arising in calculus based off of this definition. So to illustrate this, let's go ahead and let's do an example. So we're going to say, given y is equal to x to the power of 5 plus 37x, part A, we want to find dy. In other words, we want to find the differential dy. So finding the differential dy, that means I'm going to take the derivative of this function with respect to x. When I do so, we're going to get dy is equal to, take the derivative of x to the fifth, that's 5x to the fourth, take the derivative of 37x, that's going to be 37. All of this is going to be multiplied by the derivative with respect to x. In other words, we took this differential into two different pieces, or we took this derivative in two different pieces, and we're accounting for the differential change. Now, let's say that we were given this, or sorry, let's say that we found this, and now what we want to do for part B, we want to find dy, that derivative with respect to y, or sorry, that derivative for the function y with respect to x, when x is equal to 1, and dx is equal to 0.2. So what we're going to have to do at this point in time is we're going to have to then take that differential dy is equal to 5 times the quantity of 1 to the fourth plus 37, and multiply it by the change in x, which is given to us, which is 0.2. Okay, that looks pretty good here. So far we have that dy is equal to 5 plus 37. It's going to be 42. So we get 42 multiplied by 0.2, and this should get us 8.4. Therefore, the change in the y value, or the change in this function, when x is 1 and when the change in x is 0.2, that change in the y values is going to be 8.4. Awesome. So this, again, differentials allow us to observe the change in y and observe the change in x. And very similarly, just to give you a little insight here, very similarly, differentials are sort of brought forth when we're looking at linearizations. When we were looking at a linearization, the first thing that we thought of was, let's look at y minus y1 is equal to m times x minus x1. And then we said as long as your tangent line is near that function, then we're going to be able to approximate this. And so, sorry, as long as your x value is near the point in question, then you're going to be able to approximate your function f of x by the tangent line. Well, the slope of the tangent line, that was f prime, evaluated at that given point. But in this particular case, if we want it in general, then we can keep it as such. Well, this then tells me that my derivative is really equal to this. And isn't this just the slope, the change in y's over the change in x? In other words, this is your delta y over delta x is equal to f prime at x. But this is only if x is near a. And so what we could then do is we can then start decomposing this and analyzing this, that, hey, we've had this from the very beginning, and from the very beginning we could have extracted that this was the differentials that we were initially looking at. We can calculate the change in y so long as we know what the change in x is and we know the derivative of the function. So I hope that you all enjoyed this lesson, and I will see you all for the next one.